Hello, this is Milt Olson with Maintenance Technology Systems. We're here to look at our demodulation or spectral enveloping program on our MTS Explorer vibration analysis software. So we get to there by going to our select plot type and selecting demodulation. And when the program launches, it basically looks like this, and we'll leave it this size to kind of give you an idea of what's there. To kind of start off with, the cursors are all functional just like we're used to. Harmonic cursor tends to be the one that gets used the most. So you got single harmonic or sideband options there. Hertz, RPM, or orders are about the only two choices. You can include it in the report. You can change some colors, but that's really not what we're looking for. So I'm going to move this down. I generally run this with about a 2000 Hertz window. You grab the green one from the right, you can change the size of the window. The red one allows, red cursor, when you grab it, click on it and grab it, allows you to change the location of the window. Now as the demodulation works, this is kind of cool. We actually filter based on where these two cursors are at in real time. So because of the time waveform that's stored, we can do post-filtering on the waveform. It uses a bandpass filter where these cursor units are at, so we don't have to do anything different other than to just use it in the post-analysis sense. Remember, significant things I use on our analysis side. And what it does for us, there's two things I look for. The first one is this number over here. Typically, if it's below 2 is the value here in the G's RMS area, I don't get too interested in it. If it's above 2, then I do. So 1.5, it's pushing 2 a little bit. There is some interest there. Just kind of keep an eye on that one as a go, no-go gauge. And what this demodulation or spectral enveloping tends to do is that it identifies the defect frequency, or the source of the defect as a frequency. And so what I typically do, I will run this cursor down until I start to get peaks that line up pretty close. You can kind of see up here at higher, we've got our peak markers starting to come up a little bit. We've dropped just below at lower frequency. And so you kind of say, oh, I do high frequency or low frequency. They're all certainly related. And for whatever reason, demodulation tends to move that around just a little bit. And so what this means to us is that somewhere around 90 Hertz, we should expect to find a defect on this particular machine. So it's not 120 Hertz, it's not shaft speed. And so this defect is in all likelihood a bearing, and it's a 90 Hertz. So we go look at this motor speed. It's around 1775, as we can see down here. It says that if we've got a defect at 90 Hertz, it can only be a bearing, or this motor belt drives a fan, and that's what the conclusion needs to be. And so you can notice if I go to this guy, let me move it, make it a little bit smaller so I can run it over here on the side. And what happens if I change vertical, this also updates to vertical on this guy. Notice that the amplitude went down significantly in the overall, similar pattern in the defects, and axial, once again, same pattern. So as you change vertical, axial, horizontal, the demodulation changes as well. So that's about all there is to this demodulation program. Might just mention, let me pull up just a single trend, plop it here. We do have a demodulation trend that we've calculated, and sometimes it's interesting, sometimes it's not, but at least you can track the demodulation value as tracking this overall value right here over time. So anyways, take a look at that, and hope this is helpful.